Japan has built a train that flies, no wheels, no contact with the track, 310 miles per hour. The technology works and the physics are proven. The problem isn't the train, it's what flying at that speed actually demands, a path straight through the middle of a mountain range, 160 miles underground at a cost that's now hit $73 billion with no confirmed end date. Japan didn't choose the mountain because it was easy, it chose it because the coast wasn't safe. So how do you fly a train through a mountain, and what happens when the mountain won't cooperate? Let's understand why Japan is willing to make this bet. The Tokaido Shinkansen carries 160 million passengers a year, Tokyo, Nagoya, Osaka, all moving on a single coastal line. And that line runs directly above the Nankai Trough, one of the most seismically dangerous fault zones on Earth. Experts put the odds of a magnitude 8+ earthquake here at 70 to 80% within the next 30 years. When that hits, this line doesn't slow down, it shuts down for months. The estimated economic damage? $2 trillion. That's the first layer of the bet. But there's a second one. China is racing toward its own 600 km/h commercial Maglev line. The first country to open one writes the global standard and controls the contracts that follow. Japan can't afford to be second. So they're committed to that $73 billion with no confirmed end date on a route that goes inland and deep underground, deliberately chosen because the easy coastal route is the dangerous one. This isn't just a faster commute, it's a disaster-resilient backup spine for an economy that can't afford to go dark. Here's the thing, regular bullet trains run on steel wheels. Steel wheels on steel rails work great, but only up to a point. Once you try to push past 250 miles per hour, there's so much friction that the wheels get too hot, wear down, and the whole train starts to get dangerously shaky. So Japan spent 50 years working on a wild alternative. Just get rid of the wheels entirely. The solution is the SC Maglev. It uses magnets cooled to a crazy minus 269 degrees Celsius. At that temperature, they lose all electrical resistance. These magnets interact with coils in the walls of the track, lifting the train 100 millimeters, about 4 inches, off the ground. No touching, no friction, and there's no ceiling on how fast you can go. In 2015, this thing hit 603 kilometers per hour, 374 miles per hour, on the Yamanashi test track. That's a world record that still stands today. And that same track is now incorporated into the commercial route itself. But that 100mm levitation gap isn't a safety margin, it's the entire operating envelope. The guideway lining those tunnel walls has to be accurate to the millimeter across the full length of the route. 1 centimeter of geological shift in the wrong place and the system fails. Which means the mountain doesn't just have to be tunneled through, it has to stay exactly where it is, forever. So the physics are proven, the technology works, and the test track is already part of the route. But that speed creates another problem. You can't turn. At 310 miles per hour, the L0 train needs a turning radius of about 5 miles. But the land between Tokyo and Nagoya is one giant mountain range. You can't curve around the Alps when you're moving that fast. That's why they're choosing to fly at 310 miles per hour. And then there's the air pressure. When a massive train screams through a narrow tunnel that fast, it acts like a giant piston, shoving a wall of air in front of it. If you don't handle that pressure, it shoots out the end of the tunnel like a literal shockwave. That's why the L0 has that 50-foot-long nose. They spent 3 years in wind tunnels just to make sure it wouldn't cause a sonic boom every time it passed a village. The technology is ready. The physics are proven. The test track is already in the ground. So if the train is ready, why is the tunnel taking this long? The full route from Tokyo to Nagoya runs 285.6 kilometers. Of that, 256.6 kilometers go underground. Only 4.1 kilometers run at surface level. This train is essentially invisible for its entire journeys, which are basically a nightmare to build through. You've got two major active fault systems, underground rivers moving through fractured rock, and terrain that's been shifting for millions of years. And to get through all of that, Japan is digging as deep as 1,400 meters. That's the deepest tunnel Japan has ever attempted. The fault systems were mapped before a single drill turned. The water table had been studied, engineers knew broadly what was down there, and chose to build through it anyway, because staying on the coast was the riskier bet. That was the trade-off. But here's the reality. Seeing a mountain on paper and digging through it are two very different things. A big part of these mountains is made of a rock called serpentinite, and for millions of years it's been under pressure held tightly in place. The moment you drill into it and release that pressure, it reacts. It absorbs water, expands, and then starts pushing inward. Basically, the mountain starts closing in on the tunnel. So you can't just drill and move on. You have to keep reinforcing the walls constantly because the ground itself is working against you the entire time. And it gets more complicated. The terrain keeps changing, so one method isn't enough. In stable areas, they use giant boring machines. In weaker zones, they reinforce the walls immediately after digging. In the hardest rock, they use explosives. And under cities, they carefully dig beneath existing structures. It's not one clean solution, it's multiple methods stitched together into a single, perfectly aligned route. They knew this would be hard, but they didn't realize how much the mountain, and the people living around it, would push back. That squeezing rock we mentioned earlier, it was way worse than the early tests showed. It started crushing the tunnel walls so quickly that massive multi-million-dollar boring machines had to be abandoned mid-bore. The only thing that saved the project was a pilot tunnel, a smaller hole drilled ahead of the main bore to scan the geology first. It caught the problem before it became catastrophic. But the entire section still had to be fully redesigned. Years of work gone. And then there's the water. They're pumping 10,000 litres of groundwater per minute out of the Southern Alps section alone, just to keep the tunnels workable. But that water has to go somewhere, and that became the fight that nearly stopped the entire project. That water feeds into the Oi River, which 620,000 people in Shizuoka Prefecture rely on for drinking and farming. JR Central's own reports estimated the tunnel would permanently reduce the river's flow by 2 metric tons per second. And here's what made the standoff almost impossible to resolve. Shizuoka gets no station on this line. No economic benefit. Just a tunnel running under their land, draining their water. For 4 years, Shizuoka's governor blocked all construction surveys on the 8.9-kilometre section through his prefecture. No surveys, no construction. The entire 285-kilometre project held hostage by 8.9 kilometres. He resigned in April 2024. His replacement allowed surveys to begin. The standoff finally broke just a few days ago. On March 26, 2026, Shizuoka's special committee formally approved construction. The last political gate is open. While that was playing out in the mountains, the ground was moving in the city too. In October 2025, a road in Tokyo's Shinagawa ward was pushed up from below. JR Central's own tunnel boring machine had allowed compressed air to build up inside the equipment and escape through underground cracks, lifting the road surface. And the reason this is so difficult to manage? The Shinagawa station is being excavated directly below the live Tokaido Shinkansen. A decade of construction underneath hundreds of trains running overhead every single day. When the surface moved, everything stopped for months. Between the abandoned machines, the 4-year political standoff, and the surface disruptions in Tokyo, the bill kept climbing. In 2014, the original estimate was 5.52 trillion yen. By 2021, 7 trillion yen. By October last year, 11 trillion yen, around $73 billion. Nearly doubled. And that figure covers only the Tokyo to Nagoya section. The Osaka extension has no budget attached to it. And that 2027 opening date? now we're looking at 2036 at the earliest. So with the costs doubling and the ground literally moving, why hasn't Japan just walked away? Because stopping doesn't make the Nankai Trough go away. Every year Japan doesn't finish this inland route is another year the country's most critical infrastructure depends on a coastal corridor that seismologists are watching closely. And here's the math. Even with every overrun, this train costs $73 billion. A major earthquake on that coastal line costs $2 trillion. The gamble of building this train is smaller than the gamble of not building it. But if they actually pull this off, the price tag isn't the only thing that's going to change. For the people living there, the biggest shift is simply time. Tokyo to Nagoya in 40 minutes, more than cutting the current journey in half. Nagoya enters Tokyo's daily commute range for the first time, and for the alpine towns this line passes through, these are places that have been bypassed by economic development for generations. This is their first real high-speed connection to the rest of the country. But there's a much bigger picture here. This is more of a global tech race than a Japanese infrastructure project. Japan's SC Maglev technology is already licensed for a proposed line on the US East Coast, meant to connect Washington, D.C. and New York in under an hour. That project hit some serious red tape last August, but the relationship is already there. The prize is concrete. The signaling systems, the guideway specifications, the manufacturing contracts for every line that follows. Japan's clock is running, and so is China's. So here we are. It's April 2026. The project is maybe 15% complete. $73 billion committed. No confirmed opening date, and the Osaka extension, the second half of the original vision, still has no timeline and no budget. Japan committed to this before the full geological picture was known, before costs doubled, before one governor could hold it hostage for 4 years. They knew it would be hard. They didn't know how hard. At what point does a national infrastructure gamble become national infrastructure wisdom? And do you only know the difference after it opens? China is racing Japan to open the world's first commercial 600 km/h line. Subscribe and hit the bell so you don't miss it. Thanks for watching.